We're going to kick things off with function operations and transformations. This unit makes up about 1/5 of the course and seems like a good place to start because it really weaves itself through most of the other units. Before we dive into operations on functions and have a look at domain, I want to tell you that in this booklet there are 3 types of examples. The worked examples, for which the full solutions are given to you right away. Then, for the class examples and the practice problems, you'll find the full detailed solutions in your book of answers. I'll be going through the class examples with you in step-by-step solutions. The practice problems are for you to try on your own. So in Math 10C, we introduced the idea of the domain of a function. And at the time, this was actually quite complicated because we gave you lots of different functions and even relations. Piecewise functions, we gave you circles, we gave you cubics, and you weren't very familiar with these graphs. We even had discrete and continuous domains. But now in Math 30, things are a lot easier. When we say, what is the domain of a function, what we're really saying is, are there any restrictions? And fortunately, this course has only 3 possible restrictions. First, we can't divide by 0. Second, we cannot take the square root of a negative radicand. And third, we cannot take the log when the base or the argument is 0 or negative. So let's look at the worked example. In part A, we are given a rational function. The denominator divides into 2 factors, x minus 1 and x minus 2. This means if x were 1 or 2, we would have a division by 0. So 1 and 2 are non-permissible values and must be excluded from the domain. A quick reminder, in this example, the numerator would actually factor to give x plus 2 and x minus 1. So the x minus 1 at the top and bottom would cancel out, but that doesn't change that it's a non-permissible value. That just means it's a point of discontinuity rather than being a vertical asymptote. We'll get back to that later, but I wanted to mention that you don't actually need to check the numerator when checking for domain, unless of course it has a square root in it. Part B, g of x equals root 4 minus 2x. So here, we don't want to complicate things by thinking of a graph. We just want to say what values make that radicand positive or equal to 0. And so we actually write 4 minus 2x must be greater than or equal to 0. That's our statement. We're saying you must satisfy this. From here, we'll isolate the x by moving 2x over and dividing through by 2. I'll have a note in a minute about working with inequalities, but remember, if you divide through by negatives, switch the sign. I've presented the domain here also in interval notation. If we are less than or equal to 2, that means we are from negative infinity up to positive 2. We use round brackets for endpoints that are not included, such as the infinities, and square brackets for values that are included. Part C is a little bit similar to B. We have something that must be positive. The difference is, with a radical, it's okay for the radicand to be 0. With a logarithm, it's not okay for the argument to be 0. So the part in the brackets, the 2x minus 3, is called the argument. That must be strictly greater than 0. And when we solve for x, we find that x would be greater than 3/2. We could express this either in set notation or, as shown at the bottom of the screen, in interval notation. Why don't you take a minute to pause the video and try examples A through F on your own. You're going to write the domain for each function, and you can do so in either set notation or interval notation. Remember, you need to be able to interpret both. Part A. There's no square root, there's no log, so our only possibility for a restriction is a division by 0. So our restrictions lie at values of x which make the denominator 0. We'll state therefore that 4x squared minus 9 cannot be 0, and many of you would factor this as a difference of squares, 2x plus 3, 2x minus 3. An alternate solution would be to isolate the x squared by adding 9 to both sides and dividing by 4, and when we take the square root, to consider both the positive and negative case. These are the same 2 roots you would have found had you factored as a difference of squares. So our domain is x cannot be positive or negative 3/2, but is otherwise all real numbers. This one doesn't really lend itself very well to interval notation. I'll come back to that in a couple minutes. Now part B is the same as part A. There are no logarithms, there are no square roots, so we say that denominator cannot be equal to 0. The difference is that x squared plus 1 can't be factored. It's not a difference of squares, it's a sum of squares. We try to solve for x squared and we find that x squared can't be equal to negative 1, and we square root that to say, well, you can't be the root of negative 1. But wait a second, we can't square root a negative number. Don't confuse yourself here. This does not mean the question has no solutions. It means there were no solutions when we were looking for restrictions. So since there are no restrictions, the domain is actually all the real numbers. Another way to think of this, x squared, well, whether x is positive or negative, that's always going to turn out to be a positive number unless it's 0. And when you add 0 or a positive number to positive 1, it's going to be at least positive 1, meaning you cannot make that denominator 0. So for that reason, no restrictions, all real numbers. In interval notation, we write all the real numbers as from negative infinity to positive infinity, and of course, we cannot include the infinities. Part C, we can't log 0 or a negative, so the argument must be greater than 0. So if 10 minus 4x is greater than 0, and we add 4x to both sides and divide by 4, we would say that x must be less than 10 quarters. Notice as I changed the sides, I changed the direction here. This means that x is less than 5 halves, which in interval notation means we are from negative infinity up to 5 halves. Note here, it is a rounded bracket because we are not including that endpoint. Let's go back to part A for a second. The set notation of x cannot be plus or minus 3 halves really means that x is less than negative 3 halves, or that it's between negative 3 halves and positive 3 halves, or that it is greater than 3 halves. Those are all the values that are not plus or minus 3 over 2. But that's a lot to write. However, that's how you need to think of it if you wanted to write it in interval notation. Notice the use of u, which is union. That really just means the word or. Now, in 30-1, union is not part of the curriculum, so we would not have to use this notation. We would just use set notation with x not equal to plus or minus 3 halves. But this was an opportunity to explain to you that it's not that we can't represent this in interval notation, it's just that it is beyond the scope of this course. Don't let part D intimidate you. You might feel like you don't remember exponential functions and cubic functions and sinusoidal functions very well, but we don't need to right now. When we're asking about domain, we're simply wondering, is there a possibility of division by 0, the square root of a negative, or the log of 0 or negative? And in this case, there aren't any. That means the domain is all real numbers. And that's it. Part E. The moment we see a square root, we say that radicand must be greater than or equal to 0. Here, I want to warn you of a danger with inequalities. I'm going to subtract 5 from both sides. And in my next step, in order to isolate x, I would have to divide through by negative 6. Anytime I multiply or divide through by a negative number, I must change the direction of the inequality. This means that x would have to be less than or equal to 5/6 instead of greater than or equal to. In interval notation, notice that I've included the 5/6 as the right endpoint. Now part F is a little bit similar, except we've given non-numeric parameters. So ax plus b must be greater than or equal to 0. I'm going to isolate x. But here, when I was dividing, even though I had a negative b, I wasn't dividing through by a negative, so I did not change the direction of the inequality. This means that negative b over a would be my left endpoint and would be included with square brackets. Now we're going to look at operations on functions. This means taking functions given to us either as equations or graphs or charts, and then adding, subtracting, multiplying, or dividing them together. There are a few different ways we can do this, and we're going to start off with some mostly algebraic work. In this first worked example, we are given f of x equal to x squared minus 4 and g of x equal to x minus 2. And in the first part, we're asked to evaluate f times g of 3. This means the same thing as saying f of 3 times g of 3. And so if we understand function notation, we understand that means evaluate the function of f when x is 3, and evaluate the function of g when x is 3, and then multiply the two results together. So x squared minus 4 when x is 3 would look like 3 squared minus 4, giving us a value of 5. And x minus 2 evaluated when x is 3 would simply be 3 minus 2, which is 1. And 5 times 1 gives us 5. Now, though this is a pretty simple example, I'd still like to take a second to show you how to do this with your calculator. Let's go ahead and turn our calculator on and press the y equals button. Here, we'll type in y1 as being f of x. So I will type x squared minus 4. And in the y2 input, I will put in x minus 2, which is the g of x. This question wanted me to find f of x times g of x for a certain value. So in y3, I'm going to ask it to multiply f of x, which is y1, times g of x, which is y2. In order to refer to y1 and y2, I need to press this button right here that says vars. And in the variables menu, I move once to the right for y variables. And then if we press 1, we can refer to the functions y1, y2, and so on. So I will pick y1, and then I will ask it to multiply this by vars, y vars, enter, down to y2, enter. And I'm not going to bother going to a graph, although we could use that later for some examples. I'm just going to go second table. And what this question asked us to find was the value of f of 3 times g of 3. So if I move down to where x is 3, we'll see that in the y3 position, which was y1 times y2, our output value is 5. Getting back to this question, part B asks us to determine a simplified expression for h of x, which is the division of g of x by f of x. So here, I'll write g of x over f of x, and then I'll factor f of x as a difference of squares. Notice, as I cancel out that common factor, I put a 1 in the numerator, and I note the non-permissible values, including the canceled out bracket. That's really important. You have to include that one. This will serve as our simplified expression for part B. And then in part C, it's really just a continuation of part B. It asks, what would the domain be for h of x? Well, these non-permissible values represent the restrictions on our domain. And so our domain is simply that we can't be those two values, but we are otherwise all real numbers. Remember, domain asks, is there a square root that has a negative radicand? Is there a log of 0 or negative? And is there a possibility of division by 0? Here, only divisions by 0. Anytime we're combining functions and we're asked about the domain of the combined functions, we must consider the domain of each one and respect both. As an example, let's pretend that you're hosting two friends for dinner. One of your friends can't have gluten, and the other doesn't eat meat. Therefore, when cooking your meal, you'd probably make a meal that doesn't have gluten and doesn't have meat. This is the same as when we combine functions that each have their own domain. We respect both ones. Now, be careful. If we are dividing functions, that introduces new restrictions that weren't there before, which is exactly what we saw in part B. Neither f nor g had any restrictions on their domain before. They were polynomial. However, in the end, because we had a division by something, that introduced the possibility of 0 being problematic. So it wasn't a problem if f was 0 before, but it is a problem if f is 0 once it's a denominator. So watch out for that. In class example 2, we have two new functions, f of x and g of x, and we're asked first to find a simplified expression for h of x, which is the addition of f and g. In this case, I'll simply replace f of x with the appropriate expression and g of x with the appropriate expression. I put brackets here, but only for organizational purposes. Those don't actually serve any operational value. We group like terms, which means x plus x, and the negative 6 and the positive 3 go together. This is a trinomial. It does factor, but we don't care. We're not asked for any particular properties of it, except for its domain. And since it is polynomial, a quadratic in fact, we know the domain to be all the real numbers. In part B, we're asked to evaluate f minus g of 2. I find it easier to evaluate f of 2 and g of 2 separately and then subtract them. So when the f function is evaluated for 2, we find a value of 0. When the g function is evaluated for 2, we find a value of 5. 0 minus 5, remember order matters here, would be negative 5. Part C requests a simplified expression for k of x. Now, unlike last time where we had our quadratic on the bottom, here it's on the top. So when we factor this, our x plus 3's will cancel, and our remaining factor is the numerator, x minus 2. So k of x is equal to x minus 2, but again, anytime we're canceling factors that have an x involved, we must state that non-permissible value. So this would effectively be a line with a point of discontinuity. We'll talk more about the domain on the next slide, but it is simply that x cannot be negative 3. To further explain this domain for part C, we're going to graph a sketch of k of x. Now what I've done here is I've graphed f of x and g of x. And we're going to move left to right across the graph, and in each position, which is to say at each x value, we will divide the y-coordinate of fx by the y-coordinate of g of x for the same x value. So remember, f of x will be our numerator. I'm going to put some little markings in red to help us. I'm going to be dividing this height by this height. Reason being that they have the same x value, which is -4. So I'm going to divide f of -4 by g of -4. The height here would be +6. The height here would be -1. What is 6 divided by -1? It's -6. So I would put a dot right there. Next up, I would divide this height by this height. Why is that? Because both f and g have the same output when x is -3. That output is 0. Though you might say 0 over 0 is 1, you'd be incorrect. 0 over 0 is what we call an indeterminate value. So this will not generate a point, but a point of discontinuity. We'll figure out where to place it later. Let's jump to where f is at -4 and g is at +1. -4 divided by +1 makes -4. Let's jump to where x is 0. Here, f has a height of -6 and g has a height of +3. -6 divided by +3 makes -2. Maybe I'll do one more. Here, at x is 3, f has a height of 6 and g has a height of 6. 6 divided by 6 makes 1. Now that we can identify that this is a linear function, we would go ahead and draw a line through the points. However, since we found that there was one point that generated an indeterminate value when x was equal to -3, we would note this with a point of discontinuity. Remember, when a factor appears in both the numerator and denominator, that's not a vertical asymptote. It's a point of discontinuity. Class example 2 showed a division of two functions. Here, let's look at a subtraction of f minus g of x, where we'll also state the domain. Now, worth noting, f of x has a limited domain, so though it's linear, it does not start with a domain of all real numbers. This will have an effect on our combined domain later. So if I wanted to generate the graph of h of x here, the first thing I'll note is I'm going to start at x equals -2 because I'm working left to right, and because I can't start further left than that. It's not possible to combine two graphs where one of them doesn't exist. So since f of x does not exist left of -2, nothing will exist in our combined graph left of -2. So when x is equal to -2, what is the height of f and g? And remember here, it is f minus g, so this is the blue minus the green height. So the height of f is -3, and the height of g at the same x value is +3. -3 subtract +3 makes -6, so we'll put a point there. Let's jump ahead to where x is 0. Here we have a height on f of -2 and a height of g of +1. If we subtract those two values, -2 subtract 1 makes -3. Moving to where x is equal to 2. And again, I'm just jumping arbitrarily. You could go to any points. It's just these ones looked like the best integer values to work with. So where x is equal to 2, both graphs output a height of -1, so a subtraction of those two values would give 0. And then when x is equal to 4, now we get f equals 0 and g is at a height of -3. So 0 minus -3 gives us +3 as a height. You can see we're starting to notice a pattern here visually, which is that these form a linear relation. And so eventually we connect this line. In the last graph, we had a point of discontinuity, but we won't have that here because there's no division. So it has no non-permissible values. It's simply limited because the blue graph's domain was originally limited. We'll state then that since f of x had a graph of x greater than or equal to -2 and g of x was all real numbers, the combined domain would be x greater than or equal to -2. Our next work example is another opportunity to consider a combined domain. Here, f of x is already a rational function, meaning we have to consider its non-permissible value generated by the denominator. Because x plus 5 would be 0 if x were -5, we must exclude that value from the domain. G of x, however, is 3x plus 1. That's a linear function and would therefore have a domain of all real numbers. So when we combine f times g of x, we simply combine the two domains. We've not introduced a division, so there are no new non-permissible values to consider. Simply, the domain of h of x would be x cannot be -5. In part B now, we're asked to evaluate h of -4. And as we've seen in previous examples, we'll just evaluate f and g of -4 and multiply them together. Remember, h of x was defined in part A. I think that you could probably do this on your own. So what I wanted to remind us of was the fact that I can use f of x as y1, as shown in the screen down here, and g of x as y2, as shown. And then because I want to know the multiplication of the two, in y3 I would type y1 times y2. Remembering that I use the vars button to access that yvars menu, and then I choose the functions. You could either look at the graph to find what the value is when x is equal to -4 using your trace button, or you can go to your table of values and scroll up to where x is equal to -4, and there you see that y3 outputting 44. Class example 4 is another combined function, and the reason for this one is sometimes when you're asked to state the domain of k of x equal to f plus g of x, we find that students start by writing out 2x squared minus 1 plus square root 4x plus 5. And then because it looks so unfamiliar, they're not really sure what to do. But you don't need to do that. Just recognize the domain of f of x and g of x first. So f of x is a quadratic. Its domain is all real numbers. G of x is a radical function. We've looked at this many times. Here, the radicand of 4x plus 5 must be greater than or equal to 0. Subtract 5 and divide by 4 to find that x must be greater than or equal to -5/4. And that is the domain that will effectively be the domain for g of x and also for the combined function. We're then asked to evaluate k of 5. Here is where we would actually write out f of x plus g of x and then sub 5 in place of x. So 2 times 5 squared would make 50. Respect the order of operations. And we can simplify this expression down to find that our value is 54. If this were a high stakes assessment, I would encourage you again to check it in your calculator. A composition of function refers to putting one function into another function. So here we're not combining through addition or multiplication, but rather we are using the output of one function to be the input of the next. This will be things like g of f of x or f of g of x, and the order makes a big difference. Our example here is, imagine we're preparing a cake. We would first take raw ingredients, your flours and your sugars and stuff, and we would mix them together, and now we would have a dry mix. And then we would take those mixed ingredients and we put that into some sort of baking function, which would say mix with wet ingredients or stir. I'm sorry, I'm a math teacher, not a baker. In any event, once we put the raw ingredients through the mixed function, they would be outputted as mixed ingredients. We would then input the mixed ingredients into the bake function, and it would output a beautiful and delicious cake. Because after all, math is about cake. I'd like to draw your attention to this notation and point out that it means the same as this notation. Sometimes people confuse this composition notation with being a multiplication, but they are quite different. I'd also like to point out again that g of f of x is not the same as f of g of x. The order will be different. So let's look at a worked example with a composition of two functions. Here we're told that g of x is equal to 2x minus 2 and that h of x is equal to x squared minus 1. In our first part, we'll evaluate g of h of 3. We're going to start with the inside, so we're going to evaluate h of 3 first. H of 3 would be 3 squared minus 1, which gives us an output value of 8. We would then take that output value and it would become the input value for g. So now we would ask, what is g of 8? Well, g of 8 is 2 times 8 minus 2, which is 14. So g of h of 3 is 14. Part B asks us to determine the function y equals h of g of x. So now we're doing this in the other order. We're going to put g of x, which is 2x minus 2, in place of the x in the h of x function. So instead of saying x squared minus 1, we're going to say 2x minus 2 squared minus 1. Please, 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 please make use of the distributive property and write out this bracket twice. 2x minus 2 times 2x minus 2 would give you 4x squared minus 8x plus 4. Subtract the 1 and you end up with 4x squared minus 8x plus 3. Why don't you take a minute to try these before I go through them? Just pause the video. Come on, pause the video. Guys, you gotta try it on your own first. Okay, I'll do it now. Part A asks, given f of x and g of x and h of x as written on the screen, what would be the value of f of g of 6? It also asks for us to include any restrictions on domains, but that shouldn't apply when we're specifying the value. So as long as 6 works, we don't have to talk about restrictions. We will when we're involving x. So in part A, f of g of 6. Well, g of 6 means 2 times 6 minus 1. This is 11. So f of 11 now, because again, we're taking g of 6's output as our input, would be root of 11 minus 2. That's the square root of 9, which is 3. A reminder, when the square root is already written on the page, we're not talking about plus or minus. This is called the principal root, and it is uniquely positive. Now in part B, we're asked to evaluate g of x. That's kind of weird. Well, g of x was 2x minus 1. So think of that x as being the input position. And basically, we're going to input into that input position 2x minus 1. So it becomes 2 times 2x minus 1 minus 1. Just like that. We expand and simplify and end up with 4x minus 3. Now, would we have any restrictions on this domain? No. We had a polynomial function subbed into a polynomial function, which gave us a polynomial function. No worries. Let's check out part C. H of f of g of x. Whew. All right, g of x is 2x minus 1. So that goes in the inside bracket. Now we want to know, what is f of 2x minus 1? Well, that means in the place of the x in root x minus 2, we would put the 2x minus 1. This radicand can simplify to 2x minus 3. H of x then says, take whatever is the input and square it. So we're going to square this square root. Well, that simply undoes the square root and leaves us with 2x minus 3. So you might be thinking, hey, here's another linear function, polynomial. Wouldn't the domain be all the real numbers? But the answer is no, because at one point, that 2x minus 3 was a radicand, which means if it had failed to evaluate, the question would have stopped. We would not have had an output value to move forward with. So where is 2x minus 3 greater than or equal to 0? That happens when x is greater than or equal to 3/2, or 1.5. If you look on the graph, notice, different from graphing 2x minus 3, if you graph the square root of 2x minus 3 squared, your calculator will actually show that the graph does not continue left of 1.5. We've just finished a couple examples just like this one, so I'm going to leave it for you. But I want to point out it's that same idea. Don't get your domain from the last step. At every step, check. Is there a problem involving the root of a negative, a log of 0 or a negative, or division by 0? And if it happens at any step, note it in your domain. Now let's look at the domain of a composite function where we start with a rational and a linear function. So here we're given f of x equal to x over x plus 5 and g of x equal to 2x minus 1. So what would be the value of g of f of negative 4? We'll start by evaluating f of negative 4. F of negative 4 would be negative 4 over negative 4 plus 5. This is negative 4 over 1, which simplifies to negative 4. So negative 4, which coincidentally was the input value, will also be the output value as we move to the next step and input it into g of x. So g of f of negative 4 would simply be g of negative 4. And so 2 times negative 4 subtract 1 would make negative 9. In part B, we want to know what is f of g of x. Here, f of x is x over x plus 5. And in place of each of those x's, we're going to input 2x minus 1. So it's 2x minus 1 over 2x minus 1 plus 5. We'll simplify the numerator and denominator and find now that we have a rational function. This means we have to watch out for non-permissible values coming from divisions by 0. And so 2x plus 4 cannot be 0 and x cannot be negative 2. Notice in this one, we're not concerned about x being negative 5. That's because at no point did we ever see x over x plus 5. We were immediately subbing g of x in. Had this question asked the other order, g of f of x, we would have seen x plus 5 subbed somewhere, which would have led to negative 5 being a non-permissible value. And with that, we arrive at the first part of the practice questions for this section. We decided to separate functional operations from transformations just to make sure you're feeling comfortable with these before you move into a somewhat different section. I hope you'll take the time to work through these. Remember, the full solutions are in the book of answers. I also encourage you to get used to practicing with your calculator. At Rock the Diploma, we are big fans of algebra, but we don't want you to miss out on easy points that you could gain from that helpful tool beside you. Good luck. I'll see you in the next section.